So let's talk about isomers and carbohydrates. So first of all, carbohydrates are one of the four macromolecules. You have carbs, proteins, fats, and nucleotides. This is one of them. And carbohydrates consist of carbon and hydrates, so carbon and water, so carbon, oxygen, hydrogen. And you also um, have a lot of different types of carbohydrates. Of course, you have, for example, monosaccharides, which are the simplest form. Here are three examples: glucose, galactose, and fructose. Glucose and fructose can come together via dehydration synthesis and become sucrose. Glucose and galactose can come together via dehydration synthesis and become lactose. And this is very important because some people are lactose intolerant, which means when they try to ingest products containing lactose, they have trouble doing that because they don't have the enzymes to break it down, which are lactase. So they lack the enzyme lactase to break down lactose, and that makes them lactose intolerant. Okay. And of course, galactose and fructose are isomers of glucose, as you see here, and we'll talk about isomers right now. So we have two big categories. We have structural isomers and stereoisomers. On the stereoisomers, we have a bunch of subcategories. We'll talk about that later. Okay. Structural isomers, same molecular formula but different structural formulas. So for example, butane, C4H10. However, here the structure differs completely. So this is structural isomer, as you guys notice. Then let's talk about stereoisomers. So stereoisomers, these isomers have the same bond connection but different spatial arrangements. So this means that their orientation in space, in 3D space, differs. They're not the same in 3D space. So a good example is your two hands. They might look the same, but they're not the same because they cannot be superimposed on each other. So we say that these are instead mirror images of each other. Okay, same thing with these two flasks right here. Okay, so just to refresh on what this is all about, enantiomers are a type of stereoisomer, and they cannot be superimposed, and they have opposite configuration at all Carl centers. We'll look at that a little bit later. So as you see here, they have opposite configuration at all Carl centers here, okay, as you see here. Now what I want you to notice here is D-glucose and L-glucose. They are a type of enantiomer. So whenever you see something like this, it's a type of enantiomer. So D and L forms of sugars and amino acids are type of enantiomer, okay? And the number of Carl carbons determines the number of enantiomer. So let's say you have two Carl carbons, well that gives you four enantiomers. What about diastereomers? These are a type of stereoisomers that are not mirror images, and they have different configurations at some Carl centers. And oftentimes they also have different physical and chemical properties. So this is a diastereomer. This is an enantiomer. This is diastereomer. Of course, they cannot be mirror images. Just a pro tip here: if you have stereoisomer and you see that it's not an enantiomer, so it must be a diastereomer. A type of diastereomer is an epimer. Okay? So an epimer is where the two molecules are the same, but the only difference is in one stereogenic center or Carl center. So for example, right here. Here the hydroxy group is placed to the right, here is placed to the left. So this is an epimer. Okay. So try to do this task. Give a couple of examples of epimers and diastereomers. Of course, if it's an epimer, it's also a diastereomer. So here I've done that. These two are epimers, these two are epimers, these two are epimers, these two are epimers, and these D-glucose and D-cellulose are diastereomers. D-aldose and D-glucose are also only diastereomer. So if you look at an epimer, which also of course is a diastereomer, they have only one Carl carbon, so carbon 2 here and here, which is different. However, diastereomer, they have two carbons, which differs from each other. So here the hydroxy is placed to the right, here is placed to the, placed to the left, here is placed to the right, here is placed to the left, and here is placed to the right. So D-aldose and D-glucose are diastereomers only. They're not epimers. The same with D-talose and D-glucose. Okay. So let's look a little bit about D-glucose. We have Fischer projection and the more stable form here, Haworth projection. The Haworth projection is due to a nucleophilic attack here from OH to the C here in the carbonyl here. And of course, you can also name this aldohexose because you have 6 carbons, so hexose. And of course, it's an aldehyde, so we say it's an aldohexose. Okay, remember that one. Also remember that if the alcohol group reacts with the aldehyde group and it then also releases water, it's forming a hemiacetal. Okay, I'll talk about that a little bit. But before that, what is mutarrotation? So here, of course, see D-galactose. As we said, a nucleophilic attack here can come on this carbon here, and then you can form this, okay, Haworth projection. But this B isomer can also become A isomer. The only difference is in B isomer, the hydroxyl group is faced upwards here, and here it's faced downwards. So this is the A isomer and B isomer. So what is mutarrotation then? Well, in summary, mutarrotation is the process by which the specific rotation of a carbohydrate solution will change over time due to the interconversion between these two anomers. Okay, so this is the simple way to understand it. Okay, and what about hemiacetal, this hemiketal? What is these two things? So first, let's look at the formation of hemiacetal. So when aldehyde reacts with an alcohol in the presence of an acid catalyst, a nucleophilic addition occurs, and we get hemiacetal. Essentially, what ends up happening is that this one reacts with this one, and so the H here will come up here, and then you'll get the hemiacetal. Okay, you get the hemiacetal. So R1 remains here. Just to notice, water will get removed, right, as an elimination reaction. Okay, and similarly, when a ketone reacts with an alcohol in the presence of an acid catalyst, nucleophilic addition will also occur. So the oxygen atom of the carbonyl group of the ketone is attacked by the nucleophilic hydroxyl group OH of the alcohol. And so this also results in the formation this intermediate called hemiketal, which then can become a ketal, and this can become an acetal. So try and solve this one. So this one is in ketal, this B is an acetal, this one is C here hemiketal, and this is B acetal. And the reason for this, you guys can figure it out, but I'll give you a couple of tips here. For example, if we look at A here, this can either be a hemiketal or ketal. It cannot be an acetal or a hemiacetal. And the reason for this is because you see that you have three R groups, right? So you have three R groups, one here, one here, one here. Okay, so this must be, and then we also know that this must be a ketal because we don't have an OH, right? If it's hemiketal, we have OH here, but if the H gets removed and we get something different here, well then it's a ketal. So this is a ketal. Okay, we don't have a hydroxy here. Now if we look at B here, this is an hemiacetal, as I said, and the reason for that is that it cannot be ketal. Firstly, it cannot be a ketal because we have an OH here, only an OH at this carbon here. So this makes this one a hemiacetal. If you look at D here, which we said was an acetal, we see it doesn't contain a hydroxy.